Scientists just shattered physics as we know it. Could this be humanity's ticket to faster-than-light travel? In this video, we'll break down the groundbreaking discovery that could let us travel 10 times faster than light. We'll explore what scientists have uncovered, how it could work, and what it means for the future of space travel. From theory to possibility, get ready to rethink everything you know about the universe. Let's begin with a question that has defied science fiction and physics alike. Can we really travel faster than light? For decades, Einstein's theory of relativity told us no. Nothing can outrun light. Particles with mass hit a wall of infinite energy at that limit. But what if we weren't breaking that rule, just bending it? Physicists have long dreamed of shortcuts in space-time, concepts like wormholes, Alcubierre drives, and quantum tunneling. These ideas don't technically move you faster than light, but instead warp the space around you. Therefore, they offer loopholes, theoretical backdoors through Einstein's rules. Some effects, like Cherenkov radiation or superluminal shadows, look faster than light, but don't transfer information, so they don't break physics. Quantum entanglement, often hyped as spooky action, connects particles over vast distances, but still won't let us send messages across galaxies in real time. But here's where it gets wild. New experiments are pushing boundaries. Certain waveforms and quantum effects have shown phase velocities and group velocities that appear to break light speed. And in the expanding universe, galaxies already recede from us faster than light. Not because they're moving fast, but because space itself is stretching. Therefore, faster-than-light travel remains out of reach, but not entirely impossible. The future might not be about building faster engines, but learning how to bend reality itself. Now, let's begin with a mind-blowing twist. Could empty space itself unlock faster-than-light travel? According to Einstein's special relativity, nothing, not even information, can move faster than light in a vacuum. But what if that vacuum isn't truly empty? Enter the Casimir vacuum, a theoretical space between two ultra-thin metal plates placed so closely together that even light behaves differently. Physicists have speculated that in this altered vacuum state, light could travel slightly faster than its known speed, a prediction known as the Scharnhorst effect. The increase would be unimaginably small, 1 part in 10 to the 36th, but still, it opens the door to new physics. However, there's a catch. While one pair of plates may not enable faster-than-light communication due to frame limitations, multiple plate systems in motion relative to each other might. But that raises alarms about breaking causality and creating time paradoxes. Therefore, some scientists have pointed to Stephen Hawking's chronology protection conjecture, which suggests that the universe itself would prevent time travel by creating destructive energy feedback loops. The story gets even stranger with quantum tunneling. The 2008 experiment led by Eckel et al. Showed that electrons could tunnel through barriers in virtually zero time, seemingly faster than light. But even this doesn't violate relativity. As many physicists argue, the speed isn't real motion, but wave behavior and interference tricks. So, while we haven't cracked faster-than-light travel yet, these strange quantum effects suggest the universe may have secrets we've only just begun to uncover. Let's begin with the wildest possibility of all. What if the laws of physics as we know them aren't the final say? For over a century, Einstein's theory of relativity has been the unshakable backbone of modern physics. No object or signal can surpass the speed of light. But recent theoretical cracks and experimental anomalies suggest the universe might have more flexibility than we thought. One daring idea is doubly special relativity, which proposes that not just the speed of light but also the Planck length remains constant in every frame of reference. This would subtly reshape how space-time works at the smallest scales. But there's a catch. This bubble would require exotic matter with negative energy, which hasn't been proven to exist. Even if it did, generating enough of it might require energy on the scale of stars. Next, let's dive into shortcuts through space. Wormholes. Another cosmic possibility allowed by general relativity is the wormhole, a theoretical tunnel through space-time connecting two distant regions. If one could be stabilized, it might let travelers jump across the galaxy in seconds. But again, exotic matter is needed to keep such a tunnel open. Worse, using wormholes for travel risks creating closed time-like curves, which could allow time travel and all the paradoxes that come with it. To prevent that, some physicists, like Stephen Hawking, proposed the chronology protection conjecture, suggesting the universe would destroy any wormhole before it could be used to violate causality. Turning now to cosmic inflation and expanding space, interestingly, general relativity allows space itself to expand faster than light. During the early universe's inflationary period, space expanded so rapidly that objects moved apart at superluminal speeds, not because they traveled fast, but because space expanded between them. Even now, galaxies more than 14 billion light-years away appear to recede faster than light. Not due to velocity, but due to expanding space-time. Therefore, while we can't currently use this for travel, it shows that general relativity permits some forms of superluminal separation without breaking its own rules. Shifting gears to string theory and speculative physics. Some string theorists, like Gerald Cleaver and Richard Obusi, suggest that manipulating extra dimensions could create an FTL bubble. By tweaking dark energy via the 10th spatial dimension, they imagine shaping space in a way that moves a spacecraft faster than light. But, like most theories involving string dimensions, this remains highly speculative and far beyond our current technological abilities. Finally, let's acknowledge the reality check. Even if general relativity leaves room for exotic ideas like warp drives and wormholes, the consequences are huge. Most FTL concepts risk breaking causality, potentially leading to time travel and paradoxes. And since we haven't discovered exotic matter or ways to stabilize wormholes, these ideas remain theories, not technologies. That said, the math doesn't slam the door shut. It keeps it barely ajar, inviting physicists and dreamers alike to push the limits. In the end, faster-than-light travel still teeters between science and science fiction. Could quantum loopholes, warped space, or exotic particles one day crack the light-speed barrier? Or are we forever bound by the cosmic speed limit, watching, wondering, and reaching? If this made your brain spin, imagine what's next. So don't forget to like, subscribe, hit the bell, and drop your thoughts in the comments below.